Alright, so what do we need to build a laser? We need pumping, we need population inversion, we need stimulated emission, we need a cavity, and we need one partially deflecting mirror. This is what we require to build a laser. And lasers come in different kinds, different shapes, different types, different wavelengths, different energies. There's a plethora of different kinds. So this is just one example. Let me give you just two more examples of lasers. Now this is a 3-level system. Okay? You're going around like this, going up, excuse me, you're going up and immediately falling into this metastable state. Okay? Why are some states metastable? Some states are metastable simply because electrons, when they fall into the metastable state, they don't have any place to go. That's what is meant by a metastable state. So if an electron is in a metastable state, this is a metastable state because it's finding it difficult to make a transition to this lower state. That's what is meant by a metastable state from an atomic physics perspective. A metastable state is long-lived because an electron in that state has nowhere to go. It's finding it difficult to go. If it makes this downward transition, it has to forbid certain selection rules, certain angular momentum. It has to get rid of conservation of angular momentum, etc. But these are more technical details, but metastable states exist. The metastable state is rescuing us and helping us building a laser because the electrons can immediately be transferred, siphoned into this metastable state. When they're siphoned into the metastable state, they have nowhere to go, they take their time in coming back, and that's why we keep a population inversion. An electron eventually does come down, emits a photon spontaneously, and this triggers off a chain reaction of stimulated emission, and those bunch of photons now move in a massive train, all orchestrated together in perfect union, synchrony. They bounce off a mirror, come back, keep on bouncing off in the mirror, and eventually some of the light escapes out. That's our laser light. Now, this is a 3-level system. The helium-neon laser that I showed you in class is a slightly different energy level structure. And in fact, there are two gases inside helium. There's helium and neon. Both of them are inert gases. So I have a 4-level system in that case. So this is helium, this is neon. So helium will have different energy, large number of energy levels. Ruby will have a large number of energy levels, but the relevant energy levels for the lasing operation are these 3. There will be many energy levels, but the relevant ones are those 3. In helium, there are many energy levels. Helium is, by the way, the next most complicated atom after hydrogen. So we can take the Schrodinger equation and find out the potential for the helium atom and solve the Schrodinger equation. That's the best we can do analytically. Anything beyond helium, the Schrodinger equation becomes exceedingly difficult to solve with perfect ideality. So you have to resort to approximations. Anyway, for helium there is an energy level structure, and there is an energy level structure inside neon. Now helium and neon atoms, both of them are together inside the vacuum tube inside the laser cavity. What you do is you give energy to the helium electrons. They go from this state N1 to N2. So when they come here, you can't achieve population inversion between N1 and N2 because there's nothing special. Now a neon atom happens to have an energy level close to this excited energy level. This is, for the chemist, a 2p level inside helium. This energy level happens to coincide. It's very close in its energy to this excited state of the helium. So when a neon atom comes close to an excited helium atom, both of them collide. There's a mechanical collision between the helium and the neon atom. and that chemical collision transfers the energy to the neon atom, and this electron, when this energy is transferred, what's going to happen is this level is going to be populated. This electron will decay into this level by some non-radiative process. This is not an emission of a photon here. This is an emission of, say, a phonon, or it's an emission of some heat. Some collision is taking place, and this level is then excited. This level is then populated. Now this happens to be a metastable state in neon, and this state is actually another state inside the atom, which happens to be empty. Okay, and a transition can then take place between this level, and this is the lasing transition. And when an electron comes back here, it can decay back into this level. So this is a fast decay. This is a fast decay, this is a fast decay, and this is a slow decay. This slow decay corresponds to the lasing transition. Now the question that I would like to ask is it easier for this energy level structure to laze than that? Which one of these structures, energy level structures, is easy to get laser light out? Which one is easier? This one? Why? Correct, the answer is correct, but why? Sorry? This laser was made afterwards. Yes?
It's a much more simpler molecule.
Not necessarily, but yes? Not necessarily. This is a fast process here. Here we had a fast process here, and a slow process here. So we have a fast process here, fast here. So whenever the electrons fall into this level, this is a metastable state. The electrons stay here for longer, and they will eventually decay into this lower level and emit laser light. Okay? They will emit laser light, and when the electrons have fallen into this level, there's going to be fast radiative decay into this level. So why does this laser require less input of energy? This requires more input of energy. The answer is correct, which, yes.
So you have to create a state of that one state and create a state as another element of the system.
No, but that state is also provided to you by teacher. Yes. No, it's not because of time. आपने हाथ उठाया था.
The electrons are going to the upper level in another atom, and they're going to the ground state of another atom. So it's not.
This is actually not the ground state of this atom. This is some other empty energy level. It's not the ground state of the system. Yes? No. Just let me tell you, this is not a ground state. This might answer your question. This is not a ground state. This is some excited state. Yes. No. The answer lies in actually what I've written over here. Yes? Repulsion? No, these electrons are in different atoms. There's no. Yes. Is actually that's the answer. This is not a ground state of the system. This is already an excited level which already has fewer electrons. It's already an excited state. Already, to start off with, it has fewer electrons. Since it has fewer electrons to start off with, it's easy to create a population inversion between N3 and N4. Less input is required. In this case, the lasing transition is between an excited state, even though a metastable state, and the ground state. And the ground state is predominantly populated. You start off with having a large population in the ground state. So you need to pump in energy continuously to get pulses. You get pulses in this laser. You turn on the laser, it emits light, a pulse of light, and shuts off. Remains silent. Then it emits after some time when energy has picked up, it has mustered energy, gathered energy, another pulse is emitted. So the energy requirements, the input energy requirements for this laser are large. Okay? However, for this laser, it's not a pulse laser, it's a continuous laser. Or a continuous wave laser. You turn it on, it remains on. You look at the laser, you turn it on, it just remains on. Constantly on. This is a CW laser. So it's easier to laze in such a system because the lasing transition ends on an excited state rather than a ground state. And this is less populated to start off with because it's an excited state. And it's easy to achieve population inversion between N3 and N4. Now in the break, a student came up with the argument, okay, whatever you're explaining, it's a very complicated phenomenon and it just is, to me, when I learned about this, it looks flabbergasting, but it's actually beautiful. It's actually really simple, really nice when you come to think of it. And one wonders, why did it take so long to build the first laser? But why are lasers so cheap, so commonplace today? If the underlying principle is so complex, one, the beauty of physics is that complicated processes, quantum mechanics can give you useful products. The second is the question of the economy. Since you need lasers, there's a demand for lasers, the supply exists. And the supply for lasers is not lasers of this kind, these are actually simpler lasers, which are silicon based, or they are semiconductor based, not silicon based, they are semiconducting lasers. They're very cheap to make because there's a well-established industry for semiconductors. Let me spend 5 minutes on how a semiconductor laser is built. In a semiconductor laser, which is the common laser diode that you always see, we're going to have a lecture on energy bands, but let me jump the wagon and try to give an idea of what's happening over here in a semiconducting laser. So in a semiconducting laser, it's just a laser diode. We'll talk about semiconductors, so don't feel depressed if you don't know all of this. This is one crystal of some material, semiconducting material, and this turns out to be a material of this kind, gallium, aluminum, arsenide, or gallium, aluminum, indium phosphide, something of this kind. It's a crystal. And the crystal, when you make this crystal, it's made in a special way. One half of the crystal has more electrons in it. Okay, an N-type material. Does everyone know about N and P-type semiconductors?
Yes.
So the N-type, this is the N-type section of the diode. It has more electrons in it. It has 3 electrons, in other words. It doesn't have more, it has 3 electrons in it. Excess electrons that are outside the regular atomic structure, that are not bound to any atom, they are free. And this P-type section has holes in it, which are the absences of electrons. So if you build a structure, for example, if I have silicon atom here, silicon atom here, silicon atom here, and I have, say, arsenic. So silicon has 4 electrons in its valence shell, and arsenic has 5. So 4 of them contribute to making bonds with neighboring silicon atoms, and one of the electrons remains mobile. It does not participate in the bonding. So it's in the conduction band, it's not in the valence band. So this free electron I've drawn over here. And there are many free electrons because this is an N-type material. This part of the crystal is doped more with arsenic or indium, with a group 5 element. Likewise, this is doped heavily with gallium or aluminum, a group 3 element, which has an absence of an electron, which is called just one electron short of making a complete tetravalent bond. There are holes here. Now what happens is that if you connect, this structure is called a diode, and what I've drawn in the middle is a junction. This is a junction. Electrons and holes. An electron is negatively charged. A hole, which is the absence of an electron, is positively charged. They are oppositely charged particles. They can fall into one another. They can annihilate one another. They can succumb one another. And when they succumb one another, they emit energy. What happens is that in this region you get holes. Then holes diffuse into this region, and electrons diffuse into this region, and the electrons interact with the holes. They fall into the holes. Positive and negative charge, they recombine and they give off energy. It's an electron interacting with the hole and it gives off energy. Okay? So when it gives off energy, this region becomes devoid of both electrons and holes. Devoid means it's empty. It has neither electrons nor holes. So this is called a junction, and it's devoid of electrons or holes. Okay, so this is a nice concept actually, and all electrical engineers should know this. N-type material, P-type material, electrons, holes here. So inside this junction, since electrons have drifted, diffused into this junction, and holes have diffused into this junction, this material as a whole is neutral. But since electrons have been annihilated, they have interacted with holes and disappeared and given off energy, this region becomes positively charged because the electrons have gone away. This was neutral. The electrons have succumbed or have fallen prey to the recombination process, and they've gone away. So when the electrons go away, you get a positive charge. Here, the holes go away. So this side of the junction gets a negative charge, and inside the diode, a small capacitor is built. Okay? So this is junction voltage. A small voltage is built here because of this capacitor. It's like a parallel plate capacitor which is engineered into a PN junction. Now what happens in a laser diode? If you want to make a laser diode out of this, you connect this P-type to the positive terminal of the battery and the N-type to a negative terminal of the battery. What this does is that the positive terminal repels the holes, and this negative terminal repels the electrons. So more holes will jump into this barrier region, into this depletion region. This is called the depletion region. It's depleted of charge carriers. Holes will jump into the depletion region because of the bias of this potential, and electrons will diffuse into this depletion region because of the effect of this negative terminal of the battery, repulsion. Now when electrons and holes enter, fresh electrons, fresh holes enter the depletion region, they recombine once again. And when they recombine, they emit a photon. Okay? So when they emit a photon, that photon becomes the laser light. So a photon is emitted. So let me draw a third diagram to represent this emission process. So an electron and a hole recombine here. I'm just representing that recombination by this mini explosion. Okay, this is just a diagram here. The electron and the hole recombines and it gives off energy in the form of light, photons. And those photons are then emitted. And then you have inside this structure, you have a mirror here. And you have a partially reflecting mirror here. So these photons are reflected back and forth inside this so-called cavity. They're reflected back and forth. Some of these photons come out. And what we have is an LED, a light emitting diode. This is how a light emitting diode is made, an LED. And if you can have a battery, a voltage large enough, you can achieve population inversion inside this system as well. Now in order to describe this, I need to talk about bands which you don't know about. But nevertheless, I'll give you a hint. So when population inversion is achieved after a certain threshold of voltage, that LED is converted into laser. So if I draw the voltage, this voltage here, V0, versus the intensity of the output light, up to a certain range, this diode is acting like an LED, light emitting diode. It's giving off incoherent light, not laser light, incoherent light, because there is no population inversion as yet. It's incoherent light. It could be monochromatic, no doubt. Remember that the definite laser by definition is coherent. There can be other sources of light that can be monochromatic. LED can have a specific color, no doubt. You have red LEDs, now you have blue LEDs as well because of gallium nitride, which are used in the blue DVD discs, Blu-ray. So you can have specific colors of LEDs as well. But after a certain threshold voltage, the output intensity spikes up. And this is when population inversion has been achieved and you get a laser. Now in order to describe population inversion in a laser diode, I need to talk about bands, and I don't have the bandwidth to do that right now. Okay. Now, the last thing that I would like to talk about in the last 10 minutes is a really nice concept, because it's actually pushing the limits of human endeavor in science and technology. 2 Nobel Prizes at least have been awarded to this effect. One in 1997 and the other one in 2001. And this is dealing with making lasers out of atoms instead of having a beam of photons that are coherent. Why can't we have a beam of atoms? Why cannot we have a gas of atoms that is really, really cold? Why cannot we have a cold gas of atoms? Alright, so what I would like to talk about now is cooling. And what does this have to do with lasers? The connection is going to get clear in a minute. Now how do you cool objects? Put them in a refrigerator, or in a Peltier cooling, you can do Peltier cooling, or you could put in dry ice, or you could make solvent baths of acetone and isopropanol and achieve lower temperatures. Mughals used to create a cooling effect by putting salt on ice. So there are different ways of refrigeration. Then you could use liquid nitrogen. Then you could go to liquid helium. Liquid helium has a boiling point of 4.2 kelvins. But how do you get to something that's colder than that? Now what do we mean by cold or hot? Now if you have a gas, there's a law of thermodynamics which is called equipartition. Equipartition of energy. which means that the kinetic energy of an object moving along the x, which is constrained to move along the x-axis, is half mv x squared. Okay? This is related to the temperature. Okay? And this is equal to half kBT. kBT is always appearing together in an inseparable wedlock. This is the thermal energy, kBT, Boltzmann energy. This represents the amount of thermal energy. So higher the temperature, higher will be the translational kinetic energy. So now I have a soup of atoms inside a cavity, and they're all moving around in different directions. So when I cool this soup of atoms, what's going to happen is that the kinetic energy is going down and down and down. We're limiting its kinetic energy, we're decreasing its kinetic energy. Now since we have 3 degrees of freedom, we can have motion along the x-axis, y-axis and z-axis. Therefore, this is the energy in each degree of freedom, half kBT. With 3 degrees of freedom, I get 3 by 2 kBT. And this will equal the total kinetic energy, half mv squared of the object, of the atom. Which means that this is really half m vx squared plus vy squared plus vz squared, because v is really a vector. Which means I cool something means I'm arresting its kinetic energy. So what I would like to do, I would like to have a laser of atoms. I would like to have a beam of coherent atoms, which means first of all I would like to cool the atoms so that they come into the ground state. Okay, I would like to do that. I want to do quantum computing with ions. If I want to do quantum computing with ions or atoms, I would like to have them stationary, so that they don't interact with the environment. They do what they're told to do. They remain there. I want to harness them. I want to do something useful out of them, so I would like to arrest their motion first, so that I can put laser light on it or do quantum gates on it. If they're constantly moving in an erratic fashion, I will not be able to do any quantum computing with them. So there are multiple reasons of why I would need to cool atoms. And I would need to cool atoms below 4.2 kelvins. Okay, so helium has the lowest boiling point. Okay. Now, besides hydrogen. Now, what I would like to do, I would like to cool down the atoms, which means I would like to arrest their kinetic energy. Now, the point is that if you would like to go beyond this, lower than this temperature, you can actually use lasers. Now, this looks counterintuitive because a laser is a source of energy. You have lasers that can trigger fusion reactions. They are powerful sources of energy. They carry power. Laser light carries power. It can burn a metal. You have laser cutters available in the market. Lasers are, you can do inertial confinement with lasers. They are sources of fusion energy. So they are sources of energy, and they actually heat the object. If I have a laser falling on an object continuously, it's going to heat up. So how in the world can I use lasers to actually cool atoms? This is Nobel Prize winning work. Now how do we do that? Any ideas? Has anyone studied? Yes? Just a keyword so that you don't spoil the surprise. Alright, anyone else? Okay, let's use the Doppler effect. Now, does everyone know what the Doppler effect is? Okay, good. Let's use the Doppler effect. I have 6-7 minutes, so I can exploit this time. So what I have is, inside the atom I have an energy level. Okay? Now this energy is spacing, say, excuse me, is F naught. Now suppose I have a laser beam that's coming in towards the atom. And the laser beam has a frequency FL, which is not the same as F naught. is slightly detuned from f0. Okay? So this laser frequency is actually f0 plus some delta f. So if this is 100 nanometers, this is 101 nanometers perhaps. So it's slightly detuned. Okay? We'll see. Some, it could be positive, negative, but we'll see. Now what we would like to do is, let's consider one dimensions only. Suppose this atom has kinetic energy. If this atom has kinetic energy and suppose it's moving towards the laser, with the speed Vx. Now this light is coming at the speed of c, the speed of light. This is laser light. And this atom is moving towards the source of light, towards the laser with a speed Vx. Now what we would like to do is the following. This atom, if you're sitting inside the atom, the frequency of light that you see of the laser is not FL. It's going to be changed. It's going to change. By the Doppler effect, this is something you should do on your own. The frequency that is observed by the atom is F prime is not the same as FL. It's actually bigger. The frequency appears to be bigger. A source of wave that is approaching you, the frequency appears bigger. This is the Doppler effect. An ambulance that approaches you, the pitch of the siren of the ambulance appears to be higher. The frequency goes up. I hope all of you studied Doppler effect in your A level perhaps. Course mein hai na? Okay. Now you have F prime. Now this F prime is higher than FL. It's actually, you've also seen the formula, this FL over 1 minus V over C. Where V is the speed, Vx. So F prime is FL 1 minus Vx over C minus 1. Now Vx is much smaller than C. So this number is much smaller than 1. I can use the binomial expansion. I get FL 1 plus Vx over C. This is the frequency that the atom is seeing from the laser because of the Doppler effect. This is, now FL is really, it's detuned from F0, which is the atomic transition. It's F0 plus delta F. 1 plus Vx over C. Okay, let's take this first. Plus F0 Vxc plus delta F plus delta F Vxc. Now Vx over C is small, so I can ignore this. And if delta F is small, a small number multiplied with a small number is even smaller. So this means that F prime is now F0 plus F0 Vx over C plus delta F. Now the atom is seeing a frequency F0. And it's not the same as F0. So it's not, it may or may not undergo a transition. If the incoming frequency, the frequency that the atom sees exactly matches F0, only then will the electron be promoted from the lower level to the excited level. So imagine this atom is in the ground state and it's moving towards the laser source. It sees some frequency. That frequency that it actually sees must match F0. So that this electron is promoted to the higher level and the photon is absorbed. Okay? If the detuning frequency is set, delta F is set, because this is in your control. You have a laser and you can tune the wavelength of the frequency of the laser. It's in your control. You can have tunable lasers. If this delta F is set such that it's equal minus F0, because you know the atomic structure, you know F0, Vx over C, you have an estimate of Vx. If this thing is set, this is set experimentally, then this thing becomes 0 and F prime becomes equal to F naught. So now what we have under this condition, when this detuning is exactly precisely tuned to match the speed of the atom, when that happens, this electron will be promoted to the excited state. It will absorb the incoming photon. Okay? Now what happens is you have an atom. There's a photon coming in. And remember, this is just a diagrammatic representation. This photon has some momentum, doesn't it? It has momentum h over lambda. And it's in the negative direction. Let's call this the negative direction. This is the positive direction. So the incoming photon has momentum minus h over lambda. If this condition is satisfied, then what's going to happen is that an electron in the lower level is going to be excited and the photon is absorbed. When the photon is, so this atom was moving towards the right with the speed vx. When this photon is now absorbed, the photon has disappeared because it's absorbed by the system. Now what you have is an atom which is in its excited state. Now an electron which was moving with speed vx is in its excited state. But this photon has disappeared because it has been absorbed. So if I want to conserve linear momentum, what should happen to the atom? The photon has gone away. In this picture I have a linear momentum. This is the linear momentum. Now the photon has gone away. What should happen to this atom? What should happen to its momentum? It should go in the negative direction. This momentum should be transferred to the atom so that it moves towards the left. It rebounds, it changes its direction. In other words, if it decelerates. If it was moving with speed vx, it decelerates. It gets a kick of momentum delta px, which equals minus h over lambda. So its speed changes. The speed change is mass of the atom into delta Vx. This is negative. Now Vx gets a new speed, Vx plus delta Vx, and delta Vx is this thing. Its speed goes down, it decelerates. Now what it does, you have the atom already in the excited state. This atom must decay. The excited electron must come back to its ground state. And when it comes back to its ground state, it emits a photon by spontaneous emission.